Welcome to lesson 3 of the binomial expansion for year 2 pure mathematics. Today we're going to expand a plus bx to the power n, and the significance of this is, of course, it removes that restriction. Okay, so we're not just going to be dealing with expansions where the constant term is 1. We're going to hopefully expand anything we like to any real power that we like. So this is quite a powerful step. So a plus bx to the power n. We're also going to have to state the range of values of x for which the expansion is valid. And once again, I've provided you with a definition. Okay, we're still going to be using this definition today, but we're going to need to use a few tricks which we'll have up our sleeves. So please pause the video, and could you please have a go at the 4 warm-up questions. All right, to get us started, let's have a look at one part A. We're asked to factorize it in an unusual way, in the form A multiplied by 1 plus bx. Now, we have to force the first term inside the bracket to be 1. Now, the only way I can do that in the first case is if I factor out the 4. So that's the key, isn't it? All right. What I need to do is whatever this number is, that has to be my factor that's going to go outside the bracket. Okay. And the same will apply here in part B, but we'll deal with part A first. So I'm forced, by the way this factorization is designed, I'm forced to write 4 as a factor outside of the bracket. Now, if that's the case, inside the bracket, there has to be a 1 here. I have to create that 1 because that's what's required. And then I have to write down what the x term would be inside the bracket. Now, if I factored out a 4, that means I have to make this x term, so the x term here, I wanted to highlight that, the x term here, I have to make it 4 times smaller, or 4 times less, because I've factored out a 4. So the way I do that is I'm going to add, let's do it in a different color. So I'm going to have to add plus x over 4. Okay, and there we have our factorization. Now, if you want to just check that and multiply it out, you can do that just to check it, of course. So in other words, it will be 4 plus 4 times x over 4, which will be 4 plus x. So yes, it seems to work. Okay, let's try this for 1b. Now we've got the idea. We're forced, aren't we, to factor out a 2. So let's factor out the 2. That creates the 1 inside the bracket. Okay, and then I have to obviously make the 3x half as big because I've factored out a 2. So I'm going to have 1 plus 3x over 2. And if you just want to play it safe in your head, perhaps just multiply that out and check that you get 2 plus 3x. So you notice the key to this is to obviously create that 1 here and here, which will enable us hopefully to use our expansion that we've been using for the previous 2 lessons. Okay, moving on to question 2. We're told that the r plus 1th term of the binomial expansion of a plus b to the n is defined as follows. Well, yes, it is. Okay, we've seen that last year, in fact. So we have to find the 6th term. So in this instance, it's the 6th term is the r plus 1th term. So that means that my r plus 1 must equal 6 if it's the r plus 1th term. So therefore, my r value must be 5 in this case. Okay. And then also, if we just have a close look at the question, or the binomial that's about to be expanded, we have a power 8 there. So that tells me that my n is obviously going to be 8. So make a note of that. So I have everything I need, don't I? Okay. The other thing just to be clear about is what my A and my B are. So this is my A, it's an equal sign, and this is my B. So I'll write them down here. So A equals 2, and my B equals 3x. So it's a bit of revision from last year. So we have all the ingredients. So to do the expansion, we're going to have n choose r, so that's 8 choose 5. We have a to the power n minus r, so 2 to the power 8 subtract 5. And then we're multiplying that by b to the power r. So multiplied by 3x to the power r, which is of course 5. All right. Now 8 choose 5. If you can do that on your calculator, that will give you 56. Multiplied by 2 to the power 3. Multiplied by 3 to the power 5. Multiplied by x to the power 5. Okay, so we have to find the whole terms. That includes the x to the power 5. If you multiply all that together, it's a rather large number. You should discover it's 108,000. It's a huge number. 864 x to the power 5. All right, and there we go. In question 3, we have a bit more, I think, a bit of problem solving to deal with here. We can write down the definition of the term, the general term. So remember, it's n choose r. You're going to have a to the power n subtract r, and then b to the power r. Remembering, of course, that the powers have to sum to n, which they do. Now, how can we construct this x to the power 6 term? Well, there's some information there. The coefficient of x to the power 6. I'll just highlight some of this information. So x to the power 6, that's the coefficient I'm interested in. Now, to create the x to the power 6, that means that my b, which is also this bx here, has to be raised to the power 6. So let's just write down that little bit of information. So we can see clearly that the b, unfortunately in this case, is going to be equal to the bx. Okay, so don't worry about that. I know it looks a bit odd. The r is going to be 6 because I want to create the x to the power 6. Now, if we just reverse engineer this, the n is, of course, 7 because the bracket is being raised to the power 7. Okay, so let's try and build it. So we've got the 7. I'll just put that in. So we've just, okay, the r is 6. So the combination coefficient is fine. My a is, of course, 5. So I can make a note of that. Okay, so I've got 5 to the power n subtract r. Well, I can do n subtract r. That's, of course, 1. And I can also do b to the power r. And b is, of course, bx to the power r, which is, of course, 6. So everything checks out. So we've got, just to recap, we have the powers summing to 7, which is what we need. Okay, we're going to create an x to the power 6 here. And everything else should give us the total value of the coefficient. So obviously it'll be in terms of b, but there's nothing to worry about that. So you may know from experience, if you do 7 choose 6, okay, well 7 choose 7 is always 1, and 7 choose 6 is exactly the same because Pascal's triangle is of course symmetrical. 7 choose 6 is just going to be 7 because 7 choose 1 is also 7. So you may be aware of that. I don't know. You may not be. Okay. So 7 choose 6 is 7, multiplied by 5. Okay, 5 to the power 1. And then I've got to be very careful here. The bracket bx is being raised to the power 6. It's the whole thing, all of that. So I'm going to have b to the power 6. And again, this would be a common mistake. Okay, so it's b to the power 6. And that would be my coefficient. And then that's x to the power 6 for the whole term. So in other words, it's going to equal 35 b to the power 6, x to the power 6 for the x to the power 6 term. And what I don't want you to do is to get confused between when we mean term and when we mean coefficient. The coefficient of the x to the power 6 term is just this bit. Okay, it's the amount of x you have. And we're told in the question that this is equal to 2,240. So we can set up an equation now. So let's do that. So therefore, 35 b to the power 6 must equal 2,240. Divide both sides by 35 and hopefully we'll get a nice number. That's 64. Now, it says find the value of b. There are actually two values. There are more than one. You could have b equals positive or negative 2. Okay, it's not specified. So it doesn't matter in this instance. So you could have plus or minus 2. Unless there's a restriction in the question, write down all values of b. I mean, it could be that they say b is a positive constant, or b is greater than 0, or b is less than 0. So just be mindful of that. So there are actually two values for b in this instance. Moving on to question 4, we're asked to expand and simplify where possible, writing each coefficient as a fraction of a whole number. So again, this is just practicing expanding unusual brackets with more than 2 terms in them, which is what you'd be used to when you're expanding quadratics. So what I like to do, of course, is to start with the constant, which is of course 1, and then we're going to multiply everything in here by 1 and then set up some columns. So if we do that, it's going to be 1 times everything, so it's just going to be the same thing again. 1 subtract 1/2 x plus 1/8 x squared. And now I'm going to multiply everything by positive x. So all this again is going to be multiplied by positive x. Now, as you can see, I've created some columns here. So this is my x column, this is my x squared column, this is my constant column. So let's do that. So not ready for an equals yet. So x times 1 is, of course, x. So that's going to be positive x, of course. That was for that term. And then x multiplied by negative 1/2 x is, of course, negative 1/2 x squared. And then finally, x multiplying 1/8 of x squared. So that's going to be 1/8 x cubed. Okay, so let's add up vertically. And just to emphasize, I'm just going to partition my column. So we have 1 on the far left. So that's going to equal 1. We have negative 1/2 x plus x. So that's going to be plus 1/2 x. We have positive 1/8 x squared subtract 1/2 x squared. Okay, so that's 1 subtract 1/8 subtract 4/8. So that will be negative 3/8 x squared plus 1/8 x cubed. Okay, and we're finished. Now we're interested in making a further generalization of our binomial expansion that we met in the first two lessons. So we know that we're going to expand 1 plus b to the power n. And you may have noticed the limitation with this. We have been restricted so far with expanding brackets or sorry, a binomial to some power n, which could be negative or rational or both. But the constant term at the front is always 1. So we need to come up with a way of extending this definition so we can incorporate any constant, not just 1. And that's what we're going to do now. Now, we've already done some of the work in the warm-up exercise. So if I start with this, let's have a look at a plus bx first of all. So first of all, let's consider just as a linear expression as it stands. How did we create the 1 that we know we can use up here? Well, we have to come up with a factorization. So we know this is the same as, and we factor out the a, and then just think what will go inside the bracket. Well, to get a as our first term, we of course need a 1, and then we have factored out an a from the bx. So in order to balance this or compensate for this, we must divide by a inside the bracket. So this puts us in a similar position now. We've got the 1 that we wanted. What we have now got is this extra factor of a multiplying the whole bracket. Well, that's okay. We can deal with that in the binomial expansion in a moment. So let's now consider what happens when we expand this to some power n. All right, so what I'm going to do is I'm going to say, okay, so what about a plus bx to the power n? Well, it's simply what we've just discovered, but all raised to the power n. So I can take my a and my 1 plus bx over a, like that, and I'm going to raise the whole thing to the power n. I'm going to use big square brackets for this, like that. So what does this do? Well, if we know about the laws of indices, and I'll just do a little aside over here, just to confirm, if I want to raise something such as 8 to the power 2, okay, I could quite simply write this as 2 multiplied by 4 to the power 2. That's the same definition, okay? We know that 8 squared is, of course, 64. That's an equal sign. And if we consider this, we've got 2 squared and 4 squared. So this is equal to 2 squared multiplied by 4 squared. I'm just trying to convince you that this works, which is, of course, 4 multiplied by 16, which gives us the 64. So our next step is to, first of all, raise a to the power n. And then we're going to raise the bracket 1 plus b x over a to the power n, because it means the same thing. So what we now have is we have a position where we can actually do an expansion. So this is going to be a to the power n, and I'm going to open up another big square bracket here. Okay, this is This is standard notation for this. Okay, I would expect you to do this when you're doing questions of this ilk. And when we do the expansion, we can go straight to the definition up here. So we have to write down what our n and our b is. Well, this is where it gets a little bit confusing, and I probably should have chosen different notation for this, but it doesn't really matter. So this section here, including the positive, of course, this is your b. All right, so let me just make a note of that. This is equal to your b, and I realize I've used b. Okay, so I probably should have used an uppercase b, but never mind. You get the idea. And then n, of course, is just n. So all we have to do is sub in bx over a rather than subbing in b across the whole expansion. So b squared, b to the power r, etc., is going to be bx over a all squared, etc., etc. So let's do that. The first term is, of course, 1 in the expansion. Notice, of course, when I'm doing the expansion, I'm referring only to this part. Okay, this is as it was. The only difference now is that the whole thing is going to be multiplied by a to the power n. Right, let's continue. So we have 1 plus nb, so that's going to be n multiplied by bx over a, over 1 factorial, but we can dispense with that, plus n multiplied by n subtract 1 over 2 factorial, and this time my b squared is going to be bx over a all squared, and let's do one more, plus n multiplied by n subtract 1, n subtract 2 over 3 factorial, and we have bx over a all cubed, and then there'll be some more to come, and also I'm going to close the big square brackets. So never ever forget that you're going to be multiplying all of this by a to the power n. All right, that's why I write everything out in a collective step. Okay, I don't do bits of working all over the place. It's all one step. Okay, and the question evolves the whole question evolves as you move through the steps. So let's just do a couple more steps. So in other words, you're going to have a to the power n, and then inside the bracket, you're going to have 1 plus nbx over a. So it's a bit more complicated, isn't it? Plus n multiplied by n subtract 1 over 2. And then we also have b squared x squared over a squared by squaring everything inside that bracket. And then similarly, n multiplied by n subtract 1, n subtract 2 over 6, and then b cubed x cubed over a cubed, plus more to come, and then we'll just close that square bracket. Right, now, so what happens when we multiply through by a to the n? That will be the final thing that you do to tidy this up. Well, we're obviously going to start off with a to the power n. Let's write this in a different color. I did it blue again. So a to the power n. Now, because I have an a in the denominator in the second term of the expansion, this is going to reduce the power of a by 1. So I'm actually going to have plus n. I'll put the a in the numerator. So n a to the n minus 1 bx. Okay, I hope that's okay. Just draw your attention to what I've done there. So we have a to the power n, and we have an a to the power 1 in the denominator. So that gives us a to the power n subtract 1. All right, let's continue. So we're going to add, now again, I've got an a to the power n, and this time I have a to the power 2 in the denominator, so it's going to be n subtract 2. So it seems to be a pattern, as you would expect. So it's going to be n multiplied by n subtract 1, a to the power n subtract 2, all over 2, and that's going to be b squared x squared. So it looks complicated, but don't worry, once you get going, it's actually quite good. So n subtract 1, n subtract 2, I may run out of room here, over 6, and then we have a to the power n subtract 3, b cubed x cubed. Okay, and then plus more to come. So that's how we deal with this added complication, having the a here at the front as the constant in the bracket. All right, so let's have a look at some worked examples. So now we're getting close to what a full A-level question might be like. You might be asked to expand something like this. So we have to find the first 4 terms. Again, be really clear. Don't forget or highlight or make a note how many terms we actually need. And we also have to state the range of values for which the expansion is valid. Now, that's the easy bonus mark at the end. And again, please don't forget to do that. Right, so for part 1, so this is A, part I. We have to rewrite this expression so we can carry out an expansion. So the first thing to do is just to acknowledge that the square root of 4 plus x can actually be written as a power, and we know it's a rational power. So that's 4 plus x to the power 1/2. Now we've got that, as we did earlier, I just want us to consider, first of all, 4 plus x. And we need to create a constant term of 1 to replace this 4, and we do it by a factorization. So whatever that value is, like what I've just highlighted there, that has to be factored out. So if it was 3 plus x, you must factor out a 3. If it was 2 plus x, you must factor out a 2. So this is going to give us 4, and then obviously that will create the 1. That was the whole point of doing this. And then to balance things out, we have to divide our x term by 4. So they are identical expressions, one factorized, one not. Now we've done that, we can now move on to what would happen if we raise this to the power 1/2. So therefore, 4 plus x to the power 1/2 is simply, well, I say simply, it's not that simple. So I'll put everything that's inside, everything that we've just done inside these square brackets. So 1 plus x over 4. We'll close the big square bracket. And remember, this is being raised to the power 1/2. And then we use that law of indices. We have a product raised to the power 1/2. So it's the same as the powers of half, the individual factors raised to the power 1/2 as a product. In other words, we have 4 to the power 1/2 and we're multiplying that by 1 add x over 4 to the power 1/2. Now straight away, you might have to do a little calculation here. 4 to the power 1/2 is of course 2. So we'll just write that in. So this is equal to 2. And then you've got your bracket to deal with. So this is 1 plus x over 4 to the power 1/2. All right. Now we're in a position to do the expansion. So I'll just partition what I've done there, and we'll do the expansion over on the right-hand side. Give yourself plenty of room for this. Okay. Are you ready? So we've got 2 multiplied by 1 plus x over 4 to the power 1/2. Okay. Now just focusing on this binomial here. We need to write down our n, and we need to write down our b. Well, luckily there won't be any confusion here because the letters are all different. So just jot these down. So n is obviously 1/2. That's the easy bit. And b is going to be x over 4. I just recommend, even though you can see it, I recommend stating this. Write down n equals 1/2 and b equals x over 4. And that way you're clear about what you're substituting in across the expansion. You can, to some extent, ignore what I've highlighted here now. We just concentrate on the binomial expansion and sub in these two values. Right, so this is going to equal. Now, again, don't forget, this is all being multiplied by 2. I'll make a big fuss of the 2 at the front. All being multiplied by 2. So we have to do the same thing. So we have 2, and then I'm going to use big square bracket. And then we do the expansion. So we're going to have 1 plus n times b. So that's going to be 1/2 multiplied by b. Okay, I like to put things in brackets like that. It makes it clear and stops you making mistakes with signs. So 1 plus nb plus n, so that's 1/2, multiplied by n minus 1, or n subtract 1 I should say, over 2 factorial. And then we sub in our b, and it's b squared this time. So it's x over 4 squared. So that's 3 terms. We now need one more term, plus 1/2, multiplying 1/2 subtract 1, that's our n subtract 1, n subtract 2 now, all over 3 factorial, and then x divided by 4 raised to the power 3. We know there's extra, but what we can now do is close the big square bracket. And just remember our last step, we're going to multiply all of this by the 2 at the front. Now, you'll get a lot of credit for what we've done so far in terms of method marks. Now it's just a case of tidying everything up and being really careful. So we'll keep the 2 where it is for now. That's not going to be used until the very last step. And let's just carry on our normal tidying up process inside the big square brackets. So we're going to have 1. We can multiply out those fractions. That's going to be x divided by 8. And again, I don't want to do too much in one step. So that's 1/2. 1/2 subtract 1 is, of course, negative 1/2, divided by 2 factorial, which is, of course, 2. And then we can expand the brackets. That's going to be x squared over 16. Okay. And I should probably put those in brackets too, so it's all being multiplied together. Now, let's just tidy up some of this. So we have 1/2 multiplying 1/2 subtract 1, which is, again, minus 1/2. That should be the same as the coefficients you had in the 2 values you had in the previous term. Now we have 1/2 subtract 2, which is negative 3 over 2. We've done that a few times now. All over 3 factorial, which is 6. And then we have x cubed over 4 cubed, which is 64. plus more to come, which we're not interested in. Now we're getting somewhere. Well, so a couple more steps and we're there. So this is going to equal 2 multiplied by open bracket. So it's going to be 1 add x over 8. All right, now can we do something with this? Well, we have, it's going to be negative because we have negative 1/2 and every other term is positive. So it looks like I'm going to have 2 multiplied by 2 multiplied by 2 is 2 cubed. So it's going to be 8 multiplying 16. Now, if I do that, that's going to give me 128. All right, you can check that on your calculator. So it's going to be negative x squared over 128. So it's effectively 2 cubed multiplied by 16 in the denominator. Okay, please check that carefully on your calculator. Now, in the next term, let's just do a bit of forensic work before we start. So we have 2 negatives, so this is definitely going to be a positive. So I'm going to put an addition sign straight away. And it also falls into the pattern of positive, negative, and so on and so on. Now, in the numerator, we have a 3. Now, that's going to cancel with the 6 in the denominator. So I'm going to put a 2 there and a 1 there. So that means we have nothing but 1s in the numerator. So I can confidently write x cubed on top. So the question is, what's in the denominator? Well, we now have 4 powers of 2. 2 multiplied by 2 multiplied by 2 in that fraction in the numerator. 2 in the denominator, so that's 2 to the power of 4. And then multiplying the 64. Now that will give you 1024. All right, and don't be put off by these numbers. This is going to happen. You're going to get large numbers when you do this, particularly in the denominators, because we're using a as not 1. We're forced to divide by numbers like 4 and 3 and 2, and when you obviously raise those to powers, they can get quite big. And we're almost there. So the last step is just to double everything. So this is going to be 2, and then I just halve the denominators all the way along, plus x over 4, subtract x squared over 64, add x cubed over 512, plus some more to come. Okay, so that's part I. We've done that. The first 4 terms. Now we have to state the range of values for which the expansion is valid. Well, remember what we substituted in for our b. This still applies. Our b is here. Okay, it's x over 4. So we just use that as normal. So this will be a part 2. And this is the range of validity. So the range of validity is obviously everything between -1 and 1 and whatever your b is. So it's going to be -1. I'm going to sub in the b, which is x over 4. And easy enough, we just have to multiply everything by 4 and we're done. So therefore, we're going to get -4 up to, but not including 4. And there's our range of validity. Now in part B, we have a negative power. If I just write down part 2, oh sorry, B part 1, I should say. I've scrubbed it out, obviously, because I need a bit more space. You have a bit more space at the bottom of the page. So for part B, clearly we know now we're going to be looking at the expansion 2 plus 3x to the power negative 2. Right, okay. Now, as I recommended earlier, first of all, consider the binomial not raise the power. So consider 2 add 3x and how we can factorize it. Remember, we're creating the 1. The 1 will be replacing this 2 here. So that's what we have to factor out. So it's going to have to be 2 multiplying something. If this is done correctly, of course, we need a 1. And to generate the x term, remember, if we factored out a 2, that means we must divide the 3x by 2 inside the bracket. And just multiply it out. If you're not convinced by that, just multiply it out and check that it works. All right, so we've got the binomial factorized in such a way as to create the 1 so that we can use our new expansion. So now let's look at what happens when we raise this to the power negative 2. Okay, so therefore, 2 multiplying 1, add 3x over 2. Let's stick that in some square brackets. I recommend you do the same. What happens when we raise all this to the power negative 2? Well, again, we consider each factor separately. So this is going to be 2 to the power negative 2 multiplied by 1 plus 3x over 2 to the power negative 2. And we can do a bit of work here with the 2 to the power negative 2. Now, clearly, this is going to be 1 over 2 squared multiplied by 1 add 3x over 2 to the power negative 2. And again, I can simplify further. I can say that's 1 over 4 multiplied by 1 plus 3x over 2 to the power negative 2. So we now have, we're now ready to use our expansion. So again, I'm just going to partition the board. Okay, and then we'll do the expansion on the right hand side. So for this one, we have a quarter multiplying 1 add 3x over 2 to the power negative 2. I'll highlight the bit we're interested in. We're only interested in expanding this, and then the whole thing is going to be multiplied by a quarter at the end. Okay, so let's write down what our b and our n are going to be. So n is, of course, negative 2 this time, which might be a little bit easier to work with. And b is the fraction 3x over 2. Great. So let's do it. So this is going to equal 1 quarter. Open your big brackets. And let's sub our n and our b into our binomial expansion. So we have 1 plus n times b, so that's negative 2, multiplied by b, which is 3x over 2. Okay, we need 4 terms, so I need 2 more terms, plus n multiplied by n subtract 1 over 2 factorial. And that, of course, is going to be multiplied by 3x over 2 squared. Okay, and then for the final term, so we're going to add n subtract 1. I'm going to run out of room here, sorry. N subtract 2 over 3 factorial. And just to remind yourself, this is all going to be multiplied by, let me do it properly. So this is all going to be multiplied by, just put an arrow there, 3x over 2 cubed. Plus other stuff, and then close your brackets. My apologies for running out of space there. Okay, I'll better drag this across a little bit. So just put that in a little box. So this is going to equal a quarter. Okay, and then let's tidy this up. Shouldn't be too bad, this one. It's nicer not to have the fractions. Now we've got negative 2 multiplied by 3 over 2. Obviously the 2's will cancel. So we're going to get negative 3x. That's easy enough. And again, I don't want to do too much, so I'm going to say negative 2 multiplied by negative 3 over 2 factorial, which is of course 2. And then we're going to square everything inside that bracket. So that's going to be 9x squared over 4. And then the same thing for the third term. So we have negative 2 multiplied by negative 3 multiplied by negative 4 over 3 factorial, which is 6. And then if I cube everything in the bracket just next to the arrow, that's going to be 3 cubed is 27, x cubed over 2 cubed, which is 8, plus some more stuff, and then close the big square bracket. So we're nearly there. These questions are very doable. You can make mistakes, but they are quite doable. All right? If you concentrate, you'll be absolutely fine. And obviously do practice these. It's like everything else. You need to practice them so you get comfortable with the process and find your own rhythm, find your own method for doing it. Okay, as long as you set out all your working carefully and fully, then it will be absolutely fine. Right, so on to the third term now. I'm going to just do a bit of cancelling here. So we've got the 2's cancel. And that's about it. I have 2 negatives, so that's going to give me a positive. Oops, let's undo that. Undo. Okay, so that's positive. 3 times 9 is 27. X squared over 4. And then there was a lot of cancellation over in the fourth term. So the 2 and 3 will cancel with the 6 to give 1. It's 6 over 6. The negatives will cancel out. That will be positive. So this is definitely going to be a negative term here. And you can check by the pattern. We have plus, minus. So yeah, that's going to be negative. That leaves us with negative 4 over 8. Now I can actually see, I'll strike these out actually. That's going to cancel with that. So we'll have 1 and 2. Like so. So this is going to leave me with 27 again. X cubed over 2. Which isn't too bad, is it? And then we're going to add some more terms if required, but we're not required to do that. Just acknowledge that and then close off your bracket. Now, all we have to do now is multiply everything by quarter, and we've done. So this is going to equal 1/4. Okay, subtract 3x over 4. So multiply the 4's in the denominator, plus 27 x squared over 16, subtract 27 x cubed over 8 plus some more terms. And there we have our expansion. So for part 2, just very quickly, we need to state the range of validity for the expansion. Right, okay, so remember this is a bonus mark. Okay, don't forget to do it. So the range of validity, and it is part of the definition. Remember these expansions only work for a limited range of x. Okay, so just remind ourselves, it's where b is sandwiched between -1 and 1. So let's put our b in. So b is, of course, 3x over 2. Use the b you substituted in. It's another good reason to write it down. Multiply by 2, divide by 3. So it's going to be between -2/3 and 2/3. And question 1 is finished. In our worked example 2, which is our final example, we're asked to look at a function f of x, which is 2 plus kx to the power -3, and k, we're told, is a negative constant. And we're given the expansion with an unknown a, which is shown here. So we have to find the value of a. That's our task. Before we do that, if we just have a look at what information we've been given, clearly we're going to have to expand this using our new a plus bx to the power n expansion, which involves a new kind of factorization. So let's have a look at the binomial part first. So consider to add kx. Consider, in other words, we're going to think about how to factorize this. Well, this is equal to, and remember, we factor out whatever the constant value is, that becomes our factor. So we're going to have to factor out that 2. So we're going to get 2, and then we have to think about what's going to go inside the linear bracket. Well, we want the 1. The 1 is there because we need to use the expansion 1 plus b to the power n. And then just to finish it off, I have to halve my kx term to compensate for the fact I've taken 2 out as a factor. So that's our factorization, which creates the 1 that we need. Now, let's see what happens when we raise this to the power -3. Take our expression on the right-hand side and raise it all to the power -3. So I'm going to use big square brackets again for this. So 2, 1 plus kx over 2. Close those big brackets. And I'm going to include the power -3. They are essentially the same thing. Made the argument in the previous example about what happens when we raise 2 factors to the power -3. It's essentially the same as raising each individual factor to the power -3. So this is going to be 2 to the power -3 multiplied by 1 plus kx over 2 to the power -3. And of course, 2 to the power -3 is 1 over 2 cubed, which is 1 over 8. To the power -3. So we're now ready to carry out our expansion. Now we're still on part A here. I didn't actually label that, did I? This is part A, and our aim is to find the value of capital A. Well, we'll get to that. I think what we need to do first is find out what this k is. We've been given 3 terms. I think the x squared term is going to be useful in that expansion they've given us. So let's do this. So 1 over 8 multiplied by 1 plus kx over 2 to the power -3. Now, this is a really important step that I don't think I've emphasized previously. We're going to write down what n is and what our b is. So n is -3 and our b is kx over 2. Now, at no point during the rest of the lesson during the rest of the example, are you going to refer back to we dispense with that now. We're going to focus on our n as we are from this point onwards. And if we're talking about the range of validity, we're going to use the b that we just deduced here. Okay, this is the important term. So please do not go back over here and use this, because if you use that as your b, it will be wrong. The other reason it's good to write these things down is when you're doing your expansion, you've got something to refer back to. So if you keep looking at these two values and substitute those in, you're less likely to go back to the original binomial and substitute in the wrong values, because you could easily substitute in the wrong value of b for this. So let's concentrate on this bracket here, not this box here. Okay, so let's carry on with the expansion. So first thing, we're going to have to write 1/8. And then we're going to open big square brackets. Now, we're only interested in up to and including the x squared term. So that will save us a bit of work. So let's do the expansion now. So it's going to be 1 plus n times b. So that's going to be -3 multiplied by b, which is kx over 2. Okay. Then we're going to add the next term, so it's going to be -3 or n multiplied by n subtract 1 over 2 factorial, and we multiply this by kx over 2 all squared. Okay, and then there would be other terms, but we're not interested in those in this instance, but I'll just acknowledge that they're there. Right, tidying up time. So let's take out the 1/8. We've got 1 subtract 3k x over 2. And we've got just a bit of work here. -3 multiplied by -4 over 2, which is 2 factorial, and then square everything in the kx over 2 bracket. So it's going to be k squared x squared over 4 plus some more terms. Let's continue. So this time we're going to have 1 subtract 3k x over 2. We'll have a bit of cancelling. So well, I can cancel the 4s here. That's good. I think that's it. So let's just write that down. So that's going to be, it's going to be positive because we have a double negative. So it's going to be plus. And we have 3 over 2. K squared x squared. Okay. Right. So that's that. Now we just have to plus some more terms. Now we just have to divide everything by 8 or multiply by an 1/8. So this is equal to 1 over 8 subtract 3k x over 16, add 3k squared x squared again over 16. Okay, and then plus dot dot dot. I'll just put that in brackets because the actual statement above doesn't include those. All right, I think the internet cut out there. So what I've done is I've rewritten the expression that we've just got using the binomial expansion. So we can see here, just looking at our expansion, we've got 1 over 8 multiplying that bracket there is equal to the expansion on the right hand side. So let's compare coefficients. So we've been given the 1 over 8, so obviously they correspond, so this looks like it's correct. Now, we can compare the a to the negative 3k over 16. That won't do us any good because we've got two unknowns. But what we can do is we can compare the 3k squared over 16 here with the positive 27 over 16 in the expression given. So what I'm going to do is I'm going to set up a little equation using these coefficients. So if we're looking at the x squareds, we can see that 3k squared over 16 is equal to 27 over 16. So clearly we can multiply both sides by 16 and divide by 3. So therefore, k squared is equal to 9. And I'll just go back to the question. It says k is a negative constant. So if I take the root, I'm going to have to take the negative root here. Okay, we're going to dispense with the positive 3. So we have k equals negative 3. All right, now we weren't asked to find k, we were asked to find a. But we can use what we've just found and substitute it into the coefficient for x. So let's make a note of that. So sub k equals negative 3 into the coefficient for x. Let's do that up here. So this means that we have a is equal to negative 3k over 16. Just comparing those, I'll just highlight that again. So negative 3k over 16 is positive a. Substituting k equals negative 3. A equals negative 3 multiplied by negative 3 divided by 16. And we get 9 over 16 for our a value. So that's the end of part A. For part B, this is actually quite quick. And exams ask questions in a roundabout way without saying explicitly what they want. It says, determine, giving a reason for your answer, whether the binomial expansion for f of x is valid when x equals 0.1. Well, when we're talking about things being valid, obviously this is referring to the range of validity. So let's write down our range of validity for this. Now the b value, which has gone from the screen, was kx over 2. Okay, which we now know, substituting in our k, is negative 3x over 2. So if we set up the inequality, we'll get this for our range of validity. So b is between those two. Therefore, b is between negative 1 and 1. Multiply by 2, divide by negative 3. And you might want to write it in reverse so it looks better. Depends how many steps you want to do for that bit. And we get x, the range of validity for x is between negative 2/3 and 2/3. Now, to answer the question and to give a reason, we can say that 0.1 is valid since 0.1 lies in the interval minus 2/3 up to 2/3. Okay, and that would do it.